continuing our discussion on the water parameters, we will now discuss about cadmium. So, cadmium is again one of the most important chemical. It is carcinogenic, it is poisonous, it is toxic, but it is industrially a very important element, especially the gold people who manufacture gold ornaments etc. They use cadmium as one of the alloying element to fix the jewelry, pearls etc. to gold and soldering, gold soldering etc. And it is one of the important element. The average abundance of cadmium in the earth's crust is approximately 0.16 ppm. In soils it is again widely distributed and the concentration varies from 0.1 to 0.5 ppm, but you need not get worried about cadmium because it is held in the matrix, crystal matrices, and it is not easily available in the day to day crop agriculture business etc., not for the plants. In streams it is approximately about 1 microgram per liter, that is about 0.1 ppb, parts per billion, 1 parts per billion, and in groundwaters it varies from 1 to 10 microgram per liter, that is 10 ppb. So, it often exists in wastewaters discharged by electroplating. One of the cadmium is cadmium plating is widely popular and it is extremely it is used in metallurgical industries, chemical industries and other industries also. So, cadmium is extremely toxic and causes a disease known as itai, and this cadmium itai disease is similar to the one I had described to you during our discussion on mercury. Mercury causes a similar disease which attacks the central nervous system, that is known as Minamata-Bay disease, and in cadmium it is a similar disease that attacks the central nervous system. It is known as itai disease, itai. Basically it means ouch ouch in English and ayayyo in many Indian languages. So, the people who were afflicted regarding the cadmium contamination were used to shout like this, and the cadmium also comes from the fish. So, people who eat fish and fish contaminated with cadmium are the cause of itai disease. Basically it accumulates in the kidneys and liver, but prolonged intake at low levels sometimes leading to the dysfunction of the kidneys etc. are very common. So, maximum level for cadmium in irrigation water is 10 microgram per liter, that is 10 ppb, parts per billion. For drinking water it is optimum level is 10 microgram per liter. So, with this introduction I would like to tell you that there is a specific reagent for cadmium, that is known as cation. It is para-nitrobenzene diisoaminobenzene para-azobenzene, that is the chemical name of the reagent. It is purple in alkaline solution and forms an orange red complex with cadmium, and orange red complex means we should immediately imagine that the lambda max should be somewhere around between 475 and 500. The optimum for this complex is 482 nanometers. So, it is directly proportional to the concentration of cadmium present in the sample if you are working within the Beer-Lambert's range, and the linear calibration curve, that is Beer-Lambert's law range, is 0.5 to 10 microgram per milliliter of cadmium. That means 10 ppm is the determination limit, but we are saying 10 microgram is the per liter is the limit in drinking water. So, spectrophotometry is not an ideal method for the determination of cadmium for drinking water purposes, okay, potability purposes, because it is 10 times, the spectrophotometric limit is 10 times higher than this. So, normal method for the determination of cadmium is in using atomic absorption or ICP. But here what happens is, if you are able to concentrate about 1 liter to 100 ml or 1 liter to 10 ml, then the concentration will automatically increase and come in this range 0.5 to 10 microgram per milliliter, and it should be possible and to determine the cadmium. So, this is the reagent structure: cation, para-nitrobenzene, diazoaminobenzene, para-azobenzene, and this is the structure. This is a nitrate group, para-nitro, and on the para there is a azo group, and then one more amino and benzene ring, and then one azo group. So, this forms a complex with cadmium. The details of the complex can be obtained from the other reference books what I have described earlier, or you can look up the Sandel book, E.B. Sandel, Calorimetric Methods of Determination, 3rd edition. Okay. Now, with this introduction, I do not want to go into too much of details of this, because stock cadmium solution we prepare 100 ppm, details are given here. So, what we use is not cadmium chloride or something, but cadmium acetate. So, if you use cadmium acetate, your stock solution will be fairly stable, and standard calibration, standard cadmium, you can prepare it by 5 ppm, and you need Triton X100 again. It is a non-ionic surfactant. You can dissolve 1 gram of pure Triton X100 in 100 ml, and that is a Triton. Cation solution, cation is available across the shelf in from many industrial houses, laboratory suppliers, and you can prepare that in potassium hydroxide solution and 100 ml of ethyl alcohol. So, you also need sodium hydroxide 0.02 molar, and the actual reagent is a mixture of 5 ml cation, 5 ml Triton X100 and 10 ml of NaOH. So, you need a masking agent because the reaction proceeds in alkaline medium, and the masking agent is triethanolamine, again as usual, because in alkaline medium we will need triethanolamine as a complexing agent. Triethanolamine is a beautiful complexing agent for many metals including iron. And then imidodiacetate is another complexing agent, and sodium citrate. Citric acid works as a complexing agent in acidic medium, but sodium citrate works as complexing agent in alkaline medium. So, we can adjust the pH to 12 with 4% sodium hydroxide, make it up to 50 ml. Then you also need potassium sodium tartrate in the deionized water and make up to 50 ml for the complexation reactions, because many metals interfere in the determination of cadmium. So, procedure is very simple. We can transfer up to 5 ppm standard cadmium, and then you add mixed reagent 2 ml, masking agent, that is the triethanolamine, and dilute it, measure the color at 482. That means again the color is approximately orange red complex. So, you can prepare a calibration curve of up to 2 ppm and then recommended sample volume is 5 ml if you want to determine in drinking water, okay, or industrial waters. Cookbook value 0.5 ppm should give you about 0.598 plus or minus 0.02. So, if you dilute it with 0.05 ppm, that is 5 ppb should give you about 0.05 0.06 absorbance. That is also quite well within the range. So, using this reagent we have brought the determination of cadmium to spectrophotometric level with the current pollution control index. So, that is the achievement what we have done here in this case by the use of Triton X100. So, this is the spectrum of the complex, and the lambda max is somewhere around 482, and then this negative peak is for cation, excess cation. Normally in most of the spectrophotometric procedures we use excess cation or excess reagent to account for the complex formation whenever the concentration is higher. So, this is the calibration curve. You can see that we have a very good linearity, and the linearity R square value is 0.966, it is which is fairly good. So, you can see up to 0.2 ppm or even 0.1 ppm, it gives you an absorbance of about 0.2. That makes it a method, preferred method compared to atomic absorption, all because we have been trying to use Triton X100 as one of the reagents. And this is a modification we have done to the actual system, and it is very easy to determine cadmium by this method. So, now I would like to move on to another parameter, that is copper, and regarding the copper I have to tell you that copper is also a fairly widely distributed element in the nature. I would like to, I have forgotten to add, let us go back to cadmium again, because I wanted to talk to you about some of the interferences in cadmium. So, let us go back to cadmium a little bit, and in this method, this is the cadmium method, the fluoride, chloride, bromide, sulphate, nitrate, etc., they do not interfere because most of them are in the most of the time the reaction is carried out in alkaline medium. But aluminum does not interfere, but it forms a yellow colored complex. Therefore, aluminum is not, it is not possible to determine, but around 100 ppm aluminum can be tolerated. Nickel also the interferes, and then cobalt, copper, almost all these elements interfere, cobalt, copper, zinc, vanadium, and then antimony, all these things interfere. Lead does not interfere, but around that is only around 500 ppm. Basically, interference means it is an absorbance value which is not expected, or which is much more than plus or minus 10% of the standard cookbook value. Now, in this cadmium we have put 0.598 as the cookbook value. That means, if anything is 10 times, that is 0.06, we call it interference. So, if I reduce the concentration by about 10 times, if I get within the range within plus or minus 10%, we call it as non-interfering. In that aspect, with that in mind, I have to tell you that boron, lead, and arsenic, chromium do not interfere in the determination of cadmium. So, ferric again approximately 50 ppm range, that is 5 ppm, it does not interfere. Ferrous interferes always, because in alkaline medium ferrous precipitates as hydroxide. So, that is not it is not a problem, because it would have, if in your case whenever you have ferrous sample, ferrous iron in your water sample, it would have precipitated. All you have to do is just filter it and use it for the determination. Then silver up to 100 ppm does not interfere, mercury up to 100 ppm does not interfere, manganese interferes, and then molybdenum in presence of masking agent, that is Rochelle salt, because cadmium and molybdenum sometimes occur together. Therefore, we have recommended Rochelle salt for the complexation of this molybdenum, and manganese also interferes up to 10 ppm, but with Rochelle salt as a complexing agent it does not interfere. Now, this is regarding the all this what I have said so far is regarding the interference in cadmium. So, again I will go back to copper. The determination of copper, I was telling you that it is there present in the soil in wide quantities, and most of the soils are normally having iron, cobalt, nickel in very low quantities. Iron will be maximum, silica will be maximum, and aluminum will be maximum. Apart from this, some soils are rich in other micronutrients like copper, zinc, and then manganese, all these boron, etc. But the value in terms of metallurgy, metallurgically they are not of much significance because they are all in ppm levels. So, but the God has made them micronutrients, so that wherever these chemicals are there, these metals are there in slightly higher quantities, the plant growth will be profuse. So, the copper is also a fungicide. Several copper sulphate, copper oxychloride, etc. are used as fungicides in coffee and other plants in horticulture as well as agriculture. And then copper, industrially copper is a very important chemical. It is used in electroplating. 99% of electroplating work is done with copper. And the cuprous ion, normally copper is not a pollutant in actual sense, but again it imparts some sort of a raw taste to the water. So, there is a limit for the determination of copper, which I have already explained to you in the beginning, and regarding the chemistry of this principle is cuprous ion forms water soluble orange colored complex with bathocuproin disulfonate salt. So, bathocuproin is a very preferred reagent, almost specific and lovely chemical for the determination. So, the color forms in the range over a very wide range, that is 3.5 to 11, but the recommended pH range is 4 to 5, because we want to complex the many metals which may interfere using simple chemicals like EDTA, NTA, etc. The sample is buffered at a pH of 4.3 and it is reduced with hydroxylamine hydrochloride, because copper cuprous is the cuprous forms the complex with bathocuproin, not the cupric. So, absorbance is again measured around 484, that means the color is somewhat orangish red color. So, this is a very interesting sub complex. This is the copper complex with bathocuproin. You can see that bathocuproin is having nitrogen groups here, and then this is like porphyrin. See, it is a sort of tetrahedral complex, but it is like a porphyric group. There may be one or two bondings above the plane of the formation of this copper, and this is the structure of bathocuproin copper complex. So, as I had explained to you, more the number of rings, more would be the chromophore, more would be the color. So, this is basically sort of charge transfer complex only, because the most of them are electron donating groups, all the 4 nitrogens, and there are very few bonds between these two, and the method is applicable to the determination of copper for over a long range. So, obviously the reagent preparations, etc., I do not have to give you spoon feed you, but as usual our copper sulphate should be, stock solution should be around 1000 ppm, that you can dissolve it by about 0.39 gram of copper sulphate, NLR grade of course, in 100 ml of water. Your working solution can be about 100 ppm. And you will also need hydrochloric acid, hydroxylamine hydrochloride about 11%, and sodium citrate you will need about 30 gram in about 100 ml, that is about 3%, 30%, and the reagent solution should be 0.1 gram of bathocuprone disulfonic acid. So, procedure is very simple: transfer an aliquot into 10 ml volumetric flask, add HCl approximately 200 microliters, 1 ml of hydroxylamine hydrochloride, 1 ml of sodium citrate and 1 ml of bathocuprone solution mixture, and you can dilute to the mark. So, our usual practice is allow it for some time and dilute only up to develop only in 10 ml, and calibration curve is linear up to 50 microliter, 0 to 50 microliter in 10 ml volumetric flask, that works out to about 5 ppm. That is 5 microgram in 10 ml, that is 50 microgram in 10 ml, that is 5 ppm, and all other things are fairly simple, and the recommended volume is 2 ml, cookbook value is 1 ppm, gives you about 0.21 plus or minus 0.01. The significance of this is, if you want to determine copper, you prepare all the reagents and take 1 ppm of copper, and if you get 0.21 plus or minus 0.01 absorbance, your procedure is correct, your reagents are correct, your pipettes are correct, and you can go ahead with the sample preparation, with the sample analysis. So, this is the spectrum of the complex, very simple, good, nice spectrum. Bathocuprone somewhere around 480, fairly stable at the top, that means you have a slightly wide range for measurement, that means you can use a colorimeter also, you do not need only a spectrophotometer for the determination of copper. So, calibration curve, wonderful calibration curve with a linearity index of 0.999, and you can see that up to 50 microliter the absorbance is almost about 0.9, and according to our relative error concept we should not be more than 0.8 or 0.9. So, I think copper by bathocuprone is a fairly good method for the determination. Every analytical laboratory can have this bathocuprone in their stock. Next, I want to talk to you about the interference before I proceed to lead. So, among the interferences, I would like to tell you that the cadmium suffers interference from iodine, okay, but around 1000 ppm, up to 1000 ppm it does not interfere. Same thing is true with chloride, fluoride, sulphate, etc., because the analysis is being done in alkaline medium. So, many of these things will not precipitate, phosphate, bromide, etc. Nickel up to 100 ppm does not interfere, and then zinc up to 10 ppm does not interfere, vanadium up to 500 no problem, and then antimony up to 250 no problem. Yes. Chromium, ferric, ferrous, etc., up to 50 ppm there is no problem. That means equivalent quantities of chromium, nickel, etc., they can be tolerated for the determination of bathocuprone. So, it is very interesting to work with bathocuprone as a reagent for spectrophotometric determination of copper. Now, I would like to proceed for the determination of lead. Now, there are lots of things to be told about lead. For example, the lead is an element which is known to human beings since 10th century AD. We have been using lead in variety of forms, and it is widely distributed in nature. Lead is toxic by nature, and the maximum use of lead is in the preparation of in the petrol since in the last century, and only since last 10 years we have moved away from the lead culture, that is lead used to be added to petrol as an anti-knocking agent, not for diesel, but only for petrol. Nowadays, since last 10 years, lead has been removed from the petrol formulation, and instead we are using MTBE, methyl tetrabutyl ether. But still, most of the lead that was being used in petrol is distributed in the environment even now, and most of the soil, it has been as a because it is gaseous compound, it has precipitated all over the world, and every soil sample and every plant sample is contaminated with lead as of now, and including the human beings who consume the agricultural produce from the soil, as well as the non-vegetarian people who are dependent upon the terrestrial animals for their food. So, lead is toxic by injection, it is a cumulative poison. That means, if once the lead enters into your body, it keeps on adding and getting stored in the body until it starts causing problem. The toxicological nature of lead has been widely documented, and right now, as of now, the lead is part of our body, and all of us are contaminated with lead. It is very difficult to find any human, any person without lead in his body. Most of the lead is already there in the blood. So, tap waters may contain lead due to attack on lead pipes, brass fixtures and solders, etc. Lead has been used as a solder material since quite long time. So, there is no escape from the contamination of lead as far as human beings are concerned. So, we have to be very careful with respect to the lead contamination and toxic effects of lead. In groundwaters, the concentration of lead is usually less than 0.1 ppm. So, the Bureau of Indian Standards prescribes a limit of 0.05 ppm, that is 5 picograms, 5 nanograms in water, and we have chosen this pyridyl resorcinol method. Lead reacts with this reagent around pH 10 to form a red water soluble complex. The absorbance lambda max is at 520 nanometer, that is, and it is proportional to the concentration of lead. So, this is 4,2 pyridyl resorcinol, a very good reagent, and then NN group is the functional group. There is an OH here, there is one OH and there is NN group. The metal complex can form here using this nitrogen, or there are 2 OH groups. There can be a complex formation here or between this OH and this nitrogen. All these are stereospecifically controlled reactions, and usually this reaction has been studied excellently over a period of time by several excellent researchers, and most of the methods using this 4,2-pyridyl azoresorcinol are organic in nature. That is, the final product of the complex is normally extracted into organic solvents, and then analysis is completed usually in organic solvent only. Now, we have modified this procedure using only aqueous finish. So, the reagents include preparation of lead sample, that is around 1000 ppm, and then you can prepare standard lead solution of 10 ppm, that is working solution, and you have to usually prepare lead in plastic bottles, not in glass, and 4,2-pyridyl azoresorcinol, that is PAR solution, PAR 0.4%, you can dissolve it in deionized water, very easily soluble, and the reaction is in alkaline medium as usual, especially for this kind of azode products, and you have to prepare a buffer of about pH 10. The details are given here on the PPT, and the procedure involves transfer of up to 10 ppm standard solution in 10 ml volumetric flask and add reagent followed by buffer, the 4 ml etc. Those details I will not go into, but you have to measure the lambda max at 520 nanometers. The recommended volume is 2 ml, and cookbook value for 20 microgram of lead in 10 ml, that is 2 ppm, it gives you an absorbance of about 0.362 plus or minus 0.01 absorbance. So, that works out to in 10 ml, that is 2 ppm, but the limit is 0.5 ppm. So, this procedure is not really applicable for drinking water with that standard specification. So, but still we have included this because there are several industrial effluents and water samples you will have to analyze, especially with respect to lead, and wherever the concentration is higher than 2 ppm or higher than 0.2 ppm. For example, this is 2 ppm is 0.36, 0.2 ppm is 0.036. So, 0.036 is eminently measurable in drinking water etc. if the concentration exceeds, but applicability you can use this for pass or fail test. So, that is the beauty of spectrophotometry, whether the method is applicable directly to the quantitatively or not, one can first determine the qualitatively whether the concentration exceeds or not. So, the spectrum of PAR is here, PAR, and lambda max, there is a big bathochromic shift from 400 to 550, wonderful reagent, and this is somewhat orangish, yellowish, and this is red in color. And the lambda linearity is verifiable up to 50 ppm, where it goes up to 0.9, and the linearity index, that is R square value, would be 0.998. That means it is a very good straight line passing through the origin. So, now it is possible to determine the concentration of lead in drinking waters etc., but the interference of PAR is a matter of concern, because 4,2-pyridyl, as I have told you, most of these azodes react with many metals. So, lead pyridyl azoresorcinol also is not an exception to this rule, but we can take heart from the fact that fluoride, chloride etc. do not interfere, but fluoride does interfere, does not interfere up to 5 ppm, but higher values it forms a complex with lead. So, it is not very good. Cobalt, manganese, magnesium, nitrate etc. do not interfere up to 100 ppm, that is 20 times the concentration. So, we have also always made a point to test for sodium lauryl sulphate, that is most of the detergents in the aqueous in the streams, that is around 10 ppm, it does not interfere, and the iron, copper etc., they are all of them will interfere even at 100 ppm level. So, we have to make sure that the lead is separated from these elements, that is iron, copper, cadmium and then vanadium, antimony etc., and sulphate, citric acid etc., they do not interfere up to 100 ppm level. So, then there is phosphate also does not interfere, EDTH does not interfere. So, up to 50 ppm, and aluminum etc., can be tolerated up to 50 ppm. So, in general the method is applicable to for the determination of lead if the quantities of the interferent are within the equivalent range. If any of these metals are metals and anions, cations and anions exceed 100 ppm, more than 50 ppm, we will have to think about how to go about analyzing, but such situations are fairly rare. So, with this introduction I will complete our discussion on lead, and in the next class we will determine we will see how we can go about determining the total hardness and other parameters. Thank you.